MS Ramaiah University of Applied Sciences.
Hello viewers, let us discuss about the compressors. A compressor is a device that pressurizes a working fluid. One of the basic aim of compressor is to compress the fluid and deliver it to a pressure which is much higher than its original pressure. These are mechanical devices that compress gases. Compressors are an important constituent in air conditioning, either domestic or industrial applications. Even in household refrigerators that follow vapor compression refrigeration cycle, compressors are very much essential. In refinery and process industries, compressors are used for handling highly volatile gases. For example, ammonia boils at about minus 20 degrees Celsius at atmospheric pressure. Hence, the product is compressed at high pressure and stored in high pressure vessels. Compressed air is also used in utility applications like cleaning of automobile air filters. Compressed air is required in actuating pneumatic and air control valves. By varying the air pressure to the actuators of the valves, different valve opening can be achieved. Compressed air is also used in compressed air energy storage. In a power plant, during peak load times, high energy is required. During a period when there is very much less electric load, the surplus energy available can be stored in the form of compressed air. During peak load, the energy from the compressed air can be used to provide additional power. Compressor may be classified as positive displacement and dynamic compressors. Positive displacement compressors can be further subclassified as reciprocating and rotary compressors. A dynamic compressor can again be subclassified as centrifugal and axial compressor. A dynamic compressor is a continuous flow compressor characterized by rotating impeller to add velocity and thus pressure to fluid. It is widely used in chemical and petroleum refinery industry for specific services. Positive displacement compressors causes movement by trapping a fixed amount of air, then forcing or displacing that trapped volume into the discharge pipe. Reciprocating piston compressor is widely used in industries for compressed air requirement. At MSRUAS, a two-stage reciprocating piston air compressor test rig is installed for performance analysis. Before conducting the experiment, it is very important to understand the thermodynamics behind reciprocating compression. A thermodynamic state of a system is a condition identified by a set of state variables like pressure, temperature, etc. A thermodynamic process is any change that a system undergoes from one equilibrium state to another. Some of the important thermodynamic processes are isobaric process where pressure remains constant, isochoric process where volume remains constant, isentropic process where entropy remains constant, adiabatic process where there is no exchange of heat between system and surroundings, or in other words, PV to the power gamma is a constant. Isothermal process where temperature remains constant or PV is a constant. And polytropic process where PV to the power n is a constant and n is a polytropic index. A compression process can neither be isochoric nor isobaric process since there is rise in pressure with decrease in the volume. Hence, the compression process may be one among the following. If the rise in temperature and decrease in volume of the system takes place at constant temperature, then the process may be isothermal. If there is no heat transfer between system and surroundings, it can be an adiabatic process. If the adiabatic process is reversible, then the process becomes isentropic. If none of the above conditions follow, then the process can be just termed as polytropic with the polytropic index N. On a PV diagram, the isothermal lines have a lesser slope when compared to isentropic lines. The isothermal and isentropic lines can be observed in the figure. For a compression of a system from state 1 to state 2, isentropic process requires higher work input in comparison with the isothermal process. It would be more efficient if the process operated at isothermal condition. It is evident that during compression, isothermal process requires less energy when compared to isentropic process. In reality, isothermal process is practically difficult to achieve, which is possible at a quasi-static condition. An isentropic process is also not achievable since the system entropy is increasing during compression. Since the compression process happens very quickly, it can be assumed that the heat transfer between system and surrounding is negligible. Hence, the compression process can be suitably assumed to be adiabatic. The work done in a polytropic process can be written as W1 to 2 is equal to N by N minus 1 into M R T1 into P2 by P1 to the power N minus 1 by N minus 1, where N is the polytropic index, gamma if adiabatic. M is the mass of the system in kg. R is the gas constant for the gas in joule per kg Kelvin. For air, it is 287 joule per kg Kelvin. T1 temperature of the system before compression in Kelvin. P1 pressure of the system before compression in pascals. P2 pressure of the system after compression in pascals. The power output of the compressor can be calculated by replacing mass of the system by mass flow rate. Power 1 to 2 is equal to N by N minus 1 into M dot RT1 dot P2 by P1 to the power N minus 1 by N minus 1, where M dot is the mass flow rate in kg per second. As discussed before, during compression from state point 1 to 2, the work requirement in a polytropic process is considerably higher than that of isothermal process. In order to reduce the energy input for the compression process can be split into two stages with intercooling in between. A low pressure stage or LP stage where the system pressure is raised to a slightly higher pressure, that is, pressure increase from P1 to P2. Rise in pressure is accompanied with rise in temperature according to Gay-Lussac's law. The temperature rises from T1 to T2. An intercooler reduces the temperature of the system, keeping the system at the higher pressure. Temperature drops from T2 to T3, whereas pressure P3 remains same as P2. Intercooled higher pressure gas is further raised to the final high pressure in a high pressure stage or HP stage. Here, the pressure increases from P3 to P4. The compression processes can be plotted on a PV diagram. 1 to 4T represents isothermal process. If the compression happened in a single stage, the process would follow the path 1 to 4S. For the second stage compression, the system follows the path 1 to 2, 2 to 3, 3 to 4, where 1 to 2 is the first stage compression, 2 to 3 is intercooling stage, and 3 to 4 is the second stage compression. It can be observed that the work requirement is definitely reduced with two-stage compression when compared to a single stage. With multiple number of stages, work input for the compression process can be further reduced. By reducing the work input to the compressor, the efficiency of compression can be increased. At MSR UAS, a two-stage reciprocating air compressor test rig has been installed. The setup consists of LP stage, HP stage, intercooler, and an air receiver to store the compressed air. The air enters the circuit at atmospheric conditions, that is, pressure P1 and temperature T1 through an orifice. The orifice is connected to a U-tube water manometer, which can be used to calculate the discharge or volumetric flow rate of the air. The air then enters the LP stage for the first stage compression. Outlet of the first stage has both increased pressure and temperature, that is P2 and T2. This high pressure and temperature air is passed through an intercooler where the temperature of the air is reduced by keeping the pressure constant. The intercooler is an air-to-air heat exchanger. On the outside, atmospheric air is forced to move around the fins of the intercooler, which picks up heat from the hot pressurized air. Downstream of the intercooler, the pressurized air enters the HP stage for the second stage compression. Here, the pressure and temperature of the air is further increased to P4 and T4, which flows into an air receiver tank, also called as accumulator for storage. The high pressure stored air is used in adjacent labs for small utilities. Measurement of state variables are very important in this experiment. The four different state points are 1. Before LP stage, 2. After LP stage or before intercooler, 3. After intercooler or before HP stage, 4. After HP stage. From the state postulate, we know that at least two variables are required to define the state of the system. Here, the pressure and temperatures at the different states are measured using Bourdon tube gauges and thermocouples. Compressor efficiency may be defined as a ratio of compressor power output to the input power, or compressor efficiency is equal to power 1 to 2 plus power 3 to 4 by power input into 100, where power 1 to 2 is the power output of compressor in process 1 to 2 in watts. Power 3 to 4 is the power output of compressor in process 3 to 4 in watts. The input power to the compressor is calculated using the energy meter as power input is equal to N into 3600 into 1000 into eta mechanical by energy meter constant into T in watts. N is the number of blinks on the energy meter. T is the time required for N blinks in seconds. And eta mechanical is the mechanical efficiency. The volumetric efficiency of both LP and HP stage compressors can also be calculated. Volumetric efficiency of a compressor may be defined as the ratio of actual volume of air intake to the stroke volume of the piston. Volume efficiency for the reciprocating compressor is calculated with volumetric flow rates as volumetric efficiency is equal to actual volumetric flow rate by theoretical volumetric flow rate into 100, where theoretical volumetric flow rate is equal to pi d square by 4 into L into pi by 60 in meter cube by second. D is the diameter of the cylinder in meters. L is the stroke length of the piston in meters. N is the speed of the crankshaft in revolutions per minute. Specific volume, that is meter cube per kg, is calculated at all the 4 state points using the ideal gas equation. And a graph is plotted with pressure against specific volume.
Hello everyone. Today we will be conducting an experiment on a 2-stage reciprocating air compressor. Here we are having 2 stages of compression, where in one stage there will be a low pressure compression and in the other stage we will be having a high pressure compression. The air enters the system through the orifice present over here. Air from the orifice moves through this pipe and then enters the low pressure cylinder. This is the LP cylinder, where the air gets compressed to a lower pressure and then this pressurized gas enters the high pressure cylinder over here. Here the pressure of the air is further increased and then finally the high pressure air enters the accumulator over here. The compressed air at the outlet of the low pressure cylinder will be of higher pressure and higher temperature as well. So the high temperature air will be reduced of its heat through an intercooler. This is the intercooler. It's an air to air heat exchanger where the high temperature at the output of the low pressure cylinder has been reduced to about maybe 5 to 7 degrees, and then the lower temperature air enters into the HP cylinder and then the final higher pressure air goes into the accumulator. In this experimental setup we can measure 4 temperatures of the air. One temperature at the inlet of the lower pressure cylinder, another temperature at the outlet of the low pressure cylinder. Third temperature is measured at the inlet of the HP cylinder, and the fourth temperature can be measured at the outlet of the HP cylinder. All the temperatures are measured using thermocouples. The outlet pressure of the LP cylinder can be measured using this tapping, and the outlet of the HP cylinder pressure can be measured using this tapping. Both the tappings, this one for the LP pressure and this one for the HP pressure, can be measured using a board-on tube. The power input to the compressor is being given by a 3-phase induction motor. It is a 2.2 kilowatt motor, and the power is being transmitted through a belt drive. On the same shaft of both the compressor cranks, a fan is being fitted. It is an induced draft fan which will allow the air to pass over the intercooler. both the cranks of the HP cylinder and the LP cylinder is connected to a common shaft, and on the same shaft an induced draft fan is present. The pressure of the accumulator can be observed on this board-on gauge. The pressure is in terms of kg per centimeter square. On the panel of the experimental setup, we have a manometer. It is a U-tube manometer consisting of water as the manometric fluid. This manometer is used to measure the discharge of air flowing across the orifice. When the air flows across the orifice, there is a pressure drop, and that pressure drop can be seen as difference in height of the water column. We have a board-on gauge which measures the low pressure of the LP cylinder. Here the pressure is in terms of kg per centimeter square. The final high pressure of the HP cylinder output can be measured on this board-on gauge. Here also the pressure is in terms of kg per centimeter square. The speed of the shaft of both the HP as well as the LP cylinder can be measured over here. The speed can be measured in terms of revolutions per minute. As I mentioned before, we have 4 temperatures that can be measured on the setup. All the 4 temperatures can be observed on a common LED indicator. To actually see all the 4 temperatures, we can toggle using this toggle present over here. We can measure T1, T2, T3 as well as T4. The power input to the electric motor can be measured using an energy meter. Here we can note down the time required for a particular number of blinks on the energy meter, and by using suitable formula we can calculate the power input to the electric motor. Let us now start the experiment. Before starting the experiment, we have to ensure that the outlet valve of the accumulator must be completely closed. And now we will switch on the panel by starting the MCB switch. Once the MCB is switched on, we can observe that the LED on both the LED indicators is coming on. Now we shall start the compressor by switching on the motor by removing the red button. Now we can observe that there is a difference in the liquid column of the manometer. Using this height difference, we can calculate what is the actual discharge of the air flowing through the orifice into the system. We can also observe on the low pressure board-on gauge that the pressure is gradually rising. Also, there is a gradual rise in the high pressure board-on gauge as well. Once the high pressure is reaching around 2 kg per centimeter square of the pressure, then we shall take down all the readings of the temperature as well as the energy consumed by the electric motor. Now we can observe that the pressure of the high pressure cylinder is reached about 2 kg per centimeter square. At this pressure, we shall note down all the 4 temperature readings. At T1, the temperature is about 25.4. At T2, the temperature has risen to about 70.5 degrees Celsius. T3 would be after the intercooler which will show a drop in temperature of about 67.5 degrees Celsius, and T4 would be the final output temperature, which is the maximum, which is showing about 91 degrees Celsius. The speed of the shaft can be noted down using the speed indicator. It is showing a value of about 924 revolutions per minute. The energy input to the electric motor can be calculated using the energy meter. Here we take down the time for a particular number of blinks on the energy meter. The readings of low pressure, high pressure, manometer levels and the temperatures have been taken down at 2 kg per centimeter square of the HP cylinder pressure. Now this experiment can be repeated at different readings of the HP cylinder pressure. Let's say 4 kg, 6 kg and 8 kg per centimeter square of the HP cylinder pressure. Once all the readings have been taken, we can calculate what is the efficiency of the compressor, as well as we can calculate the volumetric efficiencies of each of the LP as well as the HP cylinder. That concludes the experiment.
At MSR UAS, we spark your imagination unlike any other.